Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you at my M.Sc Analytical Chemistry class. Student, I am Dr.S. Labhade, working as Associate Professor in Chemistry at College, Nashik. Student, in previous lecture we discussed the current sample polarography for increasing the sensitivity of the measurement. Under this study, we discussed that the detection limit of classical polarography can be increased up to 10 raised to minus 6 moles. In today's lecture, we discuss the derivative method of polarography. The detection limit of a classical DC polarography. Classical DC polarography is increased up to 10 raised to minus 6 moles when the current sampled program is applied for measurement. By means of modern instrument, it is possible by means of modern instrument it is possible to record the current just before the mercury drop falls from the tip of the capillary. Because instrument knows the exact drop time, and when current measurement is carried out at the end of the life of the mercury drop, when current measurement is carried out just before the drop falls. At this stage, the H drop reaches to maximum size and further growth of H drop is stopped, so that the charging current becomes constant. Charging current or non-faradic current becomes constant and the ratio of faradic to non-faradic current is increase, and the sensitivity of measurement Here the current measurement is like this. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds. If drop time is 3 seconds, then here this is the growth of mercury drop. It reaches to maximum size, and at the end of its life, the size becomes constant. Again, when drop once its size increases, it will be reaches to maximum value, and again it becomes constant. Similarly, here the size becomes nearly constant at the end of the drop life, and at that time, here this is a region. This is a measurement region. In which the non-faradic current is low. Faradic current is low. This is a drop time, and it is in second. Therefore, in this region, the non-faradic current becomes constant, and here the sensitivity is increased. And this current measurement is carried out within 5 to 20 milliseconds. This is the measurement program that is employed in current sample polarography. The current sample polarography utilizes linear potential sweep program to working electrode, to DME, that is 5 to 6 millivolt per second, and the voltammogram, but the current measurement program is discontinued, due to which the current oscillations in voltammogram are disappear. And we have a voltammogram like this. This is current in microampere versus applied EMF in volt. This is a graph, that is a polarigraph. Here like this. This is a region of residual current. And this is a region of limiting current. In this current voltage curve, that is in the current sample polarigram, the region of residual current and region of limiting current becomes noisy. Noisy in the sense that shows increase in current, though the redox reaction or reduction of analyte is not possible in this region, but we observe increase in current. As analyte is completely reduced, the region of limiting current, that But here in the region of limiting current, we observe the increasing current. Therefore, from this voltammogram, it is difficult to obtain a diffusion current by plotting a baseline becomes difficult. That means it is impossible to draw the baseline from this region or this region or this region or this region or this region. That means here plotting of baseline for calculation of a diffusion current becomes a difficult task. In the current sampled polarogram, the region of residual current and region of limiting current becomes noisy, so that it is difficult to draw the baseline needed for calculation of diffusion current or the cathodic current and the half wave potential. The current in a half wave region increases so rapidly so that the slope of the curve is get decrease, and exact value of even half cannot be determined. In this case, in this voltammogram, it is difficult to draw the baseline for determination of determination of cathodic current of the analyte, as well as the slope of the curve in this region is get changed. This is the slope, and therefore here it is difficult to determine the exact value of half wave potential. That means we can find out half wave potential from this point or this point or this point. Therefore, even half determination becomes difficult task. Here this is a drop time from this region to this region. This is a drop time. So to overcome these difficulties can be overcome by using a derivative polarogram, and the method derivative polarography. Derivative polyarogram is obtained by using this polyarogram so that we can easily determine the cathodic current required for reduction of analyte and the half-wave potential of that analyte species. Therefore, in derivative method, when current value measured in second Hg drop life is subtracted from the current value measured in first Hg drop life, and when it is divided by the difference in potential applied during the respective drop time or drop life, then we have a region then the di upon dE values are obtained, and when these are plotted against the applied potential, a derivative polarograph is obtained. Therefore, in this case, when current measurement carried out in this second step is subtracted from the current measurement carried out in first step, then that is a difference in current. When the corresponding difference of potential is taken, then it is the difference in potential. di upon dE, this ratio is obtained, and when this ratio is plotted versus the potential, continuous changing potential to the working electrode, then we have a derivative polyarogram. This polyarogram can be converted into derivative polyarogram in this fashion. Therefore, di upon dE versus E, here we have a graph in this fashion. In this case, this is the baseline which we can easily draw on this graph, potential axis. This is a half wave potential, E1 half value, and this is a peak current, or that is IP. This IP is directly proportional to concentration of analyte, and this is a half wave potential, which is the identity of the sample or analyte. Therefore, here this current sample polyarogram is easily converted into derivative polyarogram by plotting di by de versus applied EMF. Then we have a single peak curve on the voltammogram in which a peak current is directly proportional to concentration, and peak maxima corresponding to half wave potential. Another advantage of this derivative polyarogram is that when the sample containing two reducible analyte, the current sample polyarogram does not consisting of two distinct waves for two reducible analyte. That means here the analyte is reduced and we have two waves on the polyarogram, but these two waves does not obtain on the polyarogram or this voltammogram, and it is difficult to determine the exact value of a cathodic current required for the determination of analyte. Now this is a current sample voltammogram for analysis of two reducible species. Here the analyte is reduced in this region and second analyte is reduced in this region. But here sometimes we observe that this will be a reduction current for a single analyte. And by derivative technique we can easily identify this by plotting its graph as a di by de versus a E or applied EMF. Then we have a first peak for first peak for first analyte and second peak for a second analyte. Therefore, this is a E1 half for first analyte. This is E1 half for second analyte, and this is a baseline. This is ID2 and this is ID1. Therefore, two analytes that can be easily determined or easily identified if we use a derivative technique. In this graph, it is difficult to identify whether this polyarogram is for two analyte or single analyte. But derivative method directly reflect the two peaks, indicates two analytes are reduced at working electrode. And in this way, derivative method found to be superior in case of current sample polarography. And therefore, sensitivity of measurement that can be increased. Here we can identify this peak for two analyte. We easily determine their reduction current as well as half wave potential. Student, this is all about the derivative polarography and their advantages in determination of half wave potential and reduction current of the analyte. With this, we stop here. Thanks for joining me. Keep learning. Happy